Hello, I welcome you to the fifth session here. My name is Matthias Fizzi. I'm from IOHK. Let me just pass it on to the first talk, which is about blockchain and state machine replication. That's a session, and the first paper is Making Byzantine Consensus Live, and this paper is by Manuel Bravo, Gregory Chuckler, and Alexei Gotzman, and the talk will be given by Manuel. Go ahead, please.
Hi, can you hear me well? So thank you for the introduction. Byzantine Consensus is a classical program of distributed computing where several processes need to agree on a single value, while some of these processes may be malicious. So Byzantine Consensus is now used in blockchains, both with closed membership and open one. And this motivated a new way for Byzantine Consensus protocols for specifically designed for blockchain. While many are mostly concerned about safety, many of the complications actually arise from ensuring liveness. The bad news is that, as we know, we cannot make consensus both safe and live in a synchronous network. But the good news is that networks are synchronous most of the time. So people usually do the compromise of providing safety always and liveness only under synchrony. And this is captured by the partial synchrony model. So this model assumes that the execution starts in an asynchronous period where bad things can happen, like messages can be delayed or lost. And it assumes that eventually we hit a global stabilization time, or GST for short, after which the network starts behaving synchronously. So this means that the messages between non-faulty processes are delivered within an unknown time delta, and that process clocks track real time. So these Byzantine consensus protocols are usually leader driven. This means that there is a designated leader which drives the protocol. But in order to guarantee progress even under faulty leaders, so leaders that don't execute the protocol or execute it wrongly, these protocols usually divide the execution into views. So in each of the two views, there's a designated leader and the processes try to execute the protocol. So normally what people do is to rotate these leaders round robin such that once we hit GST and messages are guaranteed to get through, we eventually hit a correct leader and then we can terminate. But this is not so simple because, as I said before GST, we're assuming that bad things can happen. So in order to solve the problem of view synchronization, what we have to do is to bring all non-faulty processes into the same view, despite malicious processes trying to disrupt this. So some people opted for integrating liveness mechanisms into the core consensus protocol, but this complicates the protocol. Indeed, several existing protocols had liveness bugs, such as Tendermint. So a different approach is the modular approach. Some people introduce the concept of a synchronizer. So synchronizer is a module that tells processes when to switch views, and the core consensus protocol runs on top. So the nice thing of this approach is that we can reuse the synchronizer across different protocols, and this allows for a more systematic design. So we aim to realize this vision. One of our contributions is a synchronizer specification, which is sufficient for liveness of modern protocols. We also propose an implementation of a synchronizer that works in the most challenging variant of partial synchrony. This means a known delta and GST, and out of sync clocks and message loss before GST. Out of this list, the most challenging thing to solve is message loss. On the one hand, we could solve it by buffering messages, but the number of messages that we may need to buffer may be unbounded. So this makes the system subject to out-of-memory attacks. Our implementation only uses bounded space despite tolerating message loss. Our implementation also has low latency. That's why we call it fast sync. So by low latency, we mean that processes are synchronized rapidly after GST. And actually, we provide some precise latency analysis of this. And building on this analysis, we are able to prove precise latency about for consensus protocols. So this means that we are able to not only prove them live, but also to measure how fast they terminate after GST. And our latency analysis allows for formalizing optimistic responsiveness in an implementation independent way. As a byproduct of our research, we put a suite of protocols, of modern Byzantine consensus protocols, into a uniform framework, protocols such as HotStuff, Tendermint, PBFT, and SBFT. And we do this by removing optimizations which are meant from practical deployments and factoring out liveness mechanisms. So by putting all these protocols into this uniform framework, we are able to easily compare the protocols and to better understand the trade-offs between them. So we believe that this makes a great tutorial of modern Byzantine consensus protocols. So please check out our extended report in archive that includes all these protocols. This concludes my talk. Thank you very much. I'm ready for questions, and please watch our long version of this talk on YouTube. Thanks.
Thank you, Manuel. Any questions?
What happens if there is an asynchronous period and then a synchronous one, and then another asynchronous period? Is there like a certain length of time in which if the system is synchronous for that time, you can accomplish something nevertheless?
So the partial synchrony model doesn't assume this interleaving of asynchronous and synchronous periods. But of course, in practice, it could happen. But these protocols are meant to be live only during the synchronous period. So any progress is not guaranteed during an asynchronous period.
Any more questions? So you said out you rule out asynchronous protocols. What's so difficult about applying a synchronous protocol?
So the thing is that during asynchronous periods, you cannot guarantee progress, because essentially you don't have a bound on message delivery. And even messages can be lost during the asynchronous period. So there is no way to really guarantee, to have a deterministic protocol that guarantees liveness during asynchronous periods.
And why don't you want to resort to probabilistic protocols? Is there any inherent problem?
Well, it's just a different problem to solve, right?
Okay.
So it's still interesting, but we are looking for these strong guarantees that guarantee determinism. They guarantee finality.
Okay, thanks a lot, Manuel. I guess we're ready to switch to the next talk.
Okay, thank you very much.
And this is about leaderless state machine replication, specification, properties, and limits. This work is by Tourneur Francois Rethende and Pierre Sutra, and the talk will be given by Tourneur.
So hello everyone, my name is Tourneur. I'm a PhD student at Télécom Sud Paris, and this will be my talk on the paper on leaderless state machine replication that was written in collaboration with my advisor Pierre Sutra. So I'm going to start giving a bit of a context to ease up for you to understand the paper. So we consider modern internet services today, they often maintain more than one copy of an object. So this can be observed on the right. We'll consider this little database on the right. And each copy is located on a separate server or a replica. This is expressed by P1, P2, and P3 as an example. And we have that clients, they interact with these replicas by sending command, and they share logically these objects. And it's interesting to note that in the recent years, things have become increasingly more geographically replicated. So I put this in this example as well as the clients, they can be far away from each other. But now it begs the question, why do we replicate data? One of the reasons is for performance. So consider a client in South America, in the straight south of South America, and he needs to communicate with the service, and it's far away because the replica is in Brazil. So what we can do with data replication, we just put a replica closer to him. And another reason is for reliability. So we want to mask replica and network failure. So in the same scenario, consider that replica P4 fails. So this comment can be relayed to another replica P1 in this case. And how to replicate data? The question is, it's through the technique of state machine replication. It's interesting. It's important to notice that in the previous example, since we have multiple clients accessing and possibly modifying the object, we need to guarantee some kind of, we need some consistency criteria. And for this paper, we consider the strongest one, which is strong consistency. So how to replicate data through state machine replication? So a classic approach to state machine replication is leader-based approaches like Paxos and Raft, where commands are executed in the same order. This can be seen on the right, where the arrows indicate an ordering relationship between the commands. But there are drawbacks to this approach, which is the leader can fail. There can be some downtime, but let's not rush. Then there is an optimization over the classic SMR approach, in which it's called a generic SMR, a classical algorithm generalized Paxos, where we execute non-commuting commands in the same order. That is, you leverage commutativity, so you don't need to instantiate a consensus instance for each command. Some of them, they don't need to be totally ordered. So what is an improve over this is leaderless state machine replication, which should be the top-notch approach, especially now that we are considering geo-replication. And the previous two approaches, generic SMR and classic SMR, they are leader-driven. So in terms of combating the problem of that a leader can pose to a system, and also leverage in this approach, we also leverage commutativity. So it should be the best of all worlds, right? So this is in theory. It relies on the concept of a dependency graph. So to execute a command, we do a linearization over this graph. Notice that is a directed graph, but it's not a cyclic like in a generic SMR. And so, okay, so what is the problem? This should be a top approach. It should be all very nice, but we ran some experiments and we had some intriguing results. So we ran an experiment increasing the conflict rate for lots of for different protocols like ePaxos and Mencius, which are very well-known leaderless protocols, and the leader-driven Paxos. And true observations which were intriguing could be made is that as we increase, I plotted the cumulative distributed function here. That's what is we can see in the picture. And as the conflict rate increases, the latency of ePaxos drastically increases too. But this is not the same case for Mencius. So even though there are two leaderless protocols, we're querying ourselves why they behave so differently. So we set ourselves in this path to characterize and try to understand better these phenomena, because leaderless protocols, they're relatively a new thing. So it needs to be properly defined. So the contributions of our paper are first a theoretical framework that aims to understand and explain multiple leaderless SMR protocols. And we achieve this through a interesting and kind of simple decomposition into two services, the dependency discovery service and the consensus service. And we also propose a set of properties, leaderless SMR properties. And with these, we also provide the lower bound and upper bound results. The first one is the role theorem, which aims to explain the trade-off between reliability and scalability. It's very similar to the fast learning theorem from Lamport, but in our case, one can see in our paper that we are able to capture more precisely some protocols like ePaxos, which the fast learning theorem was not necessarily specified to deal with this kind of leaderless protocol, so we capture it more accurately. And the second contribution in terms of complexity results is the chaining effect, where we have a theorem that explains the reason for the high latency, that explains the previous phenomena from the previous slide, found in real-world implementations of leaderless protocols. So that's it. Thank you for the attention.
Thank you for your talk. Any questions out there?
Yes, one question maybe. Yes,
Go ahead.
maybe can you give an intuition how you define leaderless?
Yeah, so the main thing that one needs to take into consideration is that it relies on the fact that any replica can make progress as long as it can contact a quorum of its peers. So it's about that is really good, and also to rely on this abstraction, which is the dependency graph. So since since they can make progress at their own speed, they can diverge in the ordering between the commands, and this is captured in the dependency graph, where you can have, for example, in the example that I gave, you have a cycle between A and B and BA, because okay, this arises due to this fact that they can have different views of the ordering between these two non-commuting commands. So these are, I think, the idea that they make progress at their own speed, and as long as they contact a quorum and rely on this abstraction, I think it's a good starting point. And I would advise to check the Leaderless SMR properties in conjunction with what I just said, that you can capture. It captures quite well what it is.
Okay, thanks.
You're welcome.
Yeah, we have time for another short question.
Just to be clear, you mentioned that the latency on ePaxos went way up as you increased the conflict rate, and that wasn't the case with Mencius or Caesar?
On this case, on that experiment, we didn't run for Caesar, but it wasn't the case for Mencius, no.
So is Mencius in a different place on the trade-off that you explained in the role theorem, or is Mencius somehow immune to that trade-off? I
think Mencius is not a role optimal protocol, so I think it wouldn't be there. That would be others. There will be other trade-offs, but not the role. It doesn't abide to the role theorem. This can be checked. The protocols that actually abide to the properties can be seen at our paper. We have a table, and it's there.
Thank you. Let me transition to the next talk, which is about the paper Not a Coincidence, Sub-Quadratic Asynchronous Byzantine Agreement with High Probability. This is work by Shir Cohen, Edith Kedar, and Alexander Spiegelman, and the talk will be given by Shir.
Okay, thank you for your introduction. So I'm sure everyone that here in the session is pretty convinced why Byzantine agreement and Byzantine consensus is needed. And it's used in many large-scale systems such as Libra and Hyperledger and Algorand. It motivates both asynchrony settings and low communication complexity. So from FLP result and the Lev-Reichuk lower bound, we know that we cannot solve it in sub-quadratic and in asynchrony in any deterministic protocol. So we'll have to settle for a randomized algorithm. And this is exactly what we do. And we present the first sub-quadratic asynchronous Byzantine agreement with high probability. And when I say with high probability, I mean that both safety and liveness properties are guaranteed with probability that tends to 1 as n, the number of nodes participating in the systems, goes to infinity. And our algorithm achieves O tilde of n word complexity in expected constant time. And the main tool we are using in our work is the verifiable random function, or VRF for short, which is a pseudo-random function that provides proof of its correct computations. So you can think of someone just picking a random number along with the proof that this is indeed the number he got. And I cannot pick the number myself along with the matching proof. And we use this tool in 2 different contexts. So the first one is creating a shared randomness. So what we're trying to do, the VRF is computed locally, but by each node, and create a local sense of randomness. And we are trying to combine those into a shared randomness in the form of shared coin, where all correct processes obtain the same bit, 0 or 1, with some constant probability. And then the second context for this VRF is using is for committee sampling. So the common way to reduce complexity, word complexity, is using committees. Instead of everyone, every node talks in every round, each round of a protocol is being executed only by a subset of processes who are elected to this committee. And also explain how. And then, for example, if I was elected to the first step, then I execute what I should. And if I wasn't elected, then I just sit and wait silently until the next step arrives. And then again, we elect a new committee, and we cannot predict which nodes are going to be elected in the following steps. So the way node is elected to a committee is by also a VRF computation. So everyone computes its VRF, obtaining a number, and they have a global threshold for which if my value is below the threshold, then I'm elected. And also I have this proof from the VRF that I was indeed elected. And when I send my protocol messages, I also send the proof. So people would know to listen to me. And the problem is, what if a Byzantine process that wasn't elected also want to participate and send its own messages? But as some of you can already guess, it's not a real problem because it cannot provide the relevant proof. So it can say whatever you want, but people will ignore it. And normally in asynchronous protocols, the way nodes are continuing the protocol is by waiting to n-f messages, which is fine, right? Because we have at most f Byzantine nodes, which is great. N-f correct messages will arrive eventually. The problem is, while we compute this committee sampling, these guarantees doesn't hold anymore, because we cannot predict exactly how many nodes are elected, and we don't know how many correct processes are in it or Byzantine nodes. So what we do, we define two parameters, W and B, so that using Chernoff bounds, we can show with high probability that in each committee sampling, at least W processes in this committee are correct, and at most B of them are Byzantine. So this helps us with the progress of the protocol, but we still need some form of quorum intersection. So we derived two more properties that said that two subsets of size W will intersect by at least B+1 processes, meaning there is at least one correct processes among them. And a set of W will intersect with a set of size B+1 by 1. So just to conclude this short lecture, we present the first formalization of randomly sampled committees using cryptography in asynchronous setting. So this problem was solved before in synchronous and partially synchronous, but there it's a bit easier because you can just wait on a timeout. You don't have to ask yourself, where do I continue to run? Then we present the first sub-quadratic asynchronous shared coin and Byzantine agreement with high probability algorithms that has expected O and word complexity. That's it. Thank you. I'll take questions if you have.
Thanks for your talk. Questions? Jennifer?
Yes, thanks for the nice talk. Is anything known about lower bounds on the word complexity?
So we have the, as I mentioned, the Dolev-Raichuk lower bound. So we know deterministically we cannot solve it. But beyond that, I'm not familiar with any other. Oh, sorry, there is one by Abraham et al. That expand the Dolev-Raichuk one to the randomized model, where they also say you need a quadratic if you have something that calls no after defect removal. So they do it in synchronous setting, and we try to adapt it into the asynchronous settings.
Another question?
There's one in the chat. I'll read it for all of you. So basically, you try to do what is done in sortition of Algorand, but in asynchronous way. So yeah, exactly. We're trying to overcome what they solve using timeout and doesn't work in asynchrony. We're trying to expand it.
Hi, I watched the full presentation earlier, And I got a bit confused regarding the first phase when you did the random coins, because it said that you wait for n-f results and then send the minimum of those. And that would be the result of n-f nodes or something. It felt like two completely different things.
You're talking about the lecture on YouTube, I guess?
Yes.
Yeah, so we are presenting it, we're starting with step one is trying to implement our logic into a non-committee sampling way where we can wait for n-f. And then indeed we encounter this problem of n-f. So instead we wait for W on this exact step when moving to committees.
But if you then get the minimum value, that one has only been sent by one of the nodes, or is multiple nodes sending the same value, even though it's random?
It would be the minimum value of all the initial values from the first step. So only the first committee will execute the VRF for obtaining some random numbers. And then all the other participants will continue the game with the initial values.
Yeah, okay. Okay, thank you.
So it seems your tolerance bound is not optimal, most likely. Are you just happy with this result, or are you trying to get it tight?
So our resilience, I'll just let everybody know, it is of almost a third. We have this epsilon in this definition. We have n equals to third minus epsilon n. And we could not overcome it due to when we wanted to bound the constant probability of the coin. So we could not find a way around it. But if any of you could, so that would be great.
Also, I saw this 4.5 threshold.
Right.
Is that, did I get that totally wrong? T less
No,
than,
it's right.
Okay.
It's because we have this all sort of computations that of the constant probability of the coin, and then we want to keep it positive. So we have to.
Oh, okay. So you have to expand. Okay. Thanks a lot, Shira. We're going to the next talk, which is about expected linear round synchronization, the missing link for linear Byzantine SMR. This is work by Odette Nao and Edith Guédra, and the talk will be given by Odette. Go ahead, please.
So, hi everyone. First, I want to excuse my bad hair condition. We're under a lockdown here in Israel, so the barbershops are closed. So I'm sorry for the horrific images you might be seeing. But today I'll present the paper that was, thank you for the introduction, and I'll go straight and talk. We're talking about the eventually synchronous model in the Byzantine SMR problem. There is a no lower bound, Shir mentioned it, from 1982 of a quadratic number of messages for worst case deterministic Byzantine agreement. And if we look at some of the results over the history, we can see that DLS actually requires a cubic number of messages to reach a decision, followed by PBFT and Ziziva, which required a quadratic number of messages. And since the era of blockchains, we have protocols like Tendermint and Hotstuff, which actually require a linear number of messages per decision. Now, you might wonder what's the connection between this linear message complexity and the well-known lower bound, quadratic lower bound. And the answer is that it takes a linear number of messages to reach a decision only after some condition is met. The condition is that 2f+1 correct processes follow a correct leader. So existing round synchronization, this is the condition is what we call round synchronization. And the techniques for round synchronization, even ones that use randomness, are not linear. So in this work, we are actually the first ones to give an expected linear round synchronization protocol, which helps to solve Byzantine SMR protocols like Hotstuff with linear message complexity. So how do we use this round synchronization? If we look at an example, we know that most SMR protocols are divided into rounds or views, and the process is always in some round. Now, progress is guaranteed once 2f+1 correct processes are in the same round. So if we take a look at an example, the axis here represents the round number, And let's say that we use an SMR algorithm to maintain a blockchain. So we have F+1 correct processes in round 4, and let's say that F Byzantine processes are currently cooperating with them. So once we have two F+1 processes which cooperate, they can run the SMR protocol and reach a decision, add a new block, move to the next round. Again, run the consensus protocol, make a decision, add a new block, and move to the next round. And let's assume now that the F Byzantine processes stop to drink a margarita and stop cooperating with the correct processes. So now we're left in a situation where we have F+1 correct processes in round 6, F correct processes which are stuck somewhere behind. And the intuition behind round synchronization is how do we synchronize all those correct processes to the same round. So round synchronization means to synchronize all the correct processes eventually to the same round, and having the leader of that round a correct process. So how do we use round synchronization to actually solve Byzantine SMR? For this, I'll quote directly from the hot stuff paper. Theorem 4 states the following. It basically says that after GST, there exists some time period TF, and if all correct replicas remain in the same round V during TF time, and also the leader of that round is correct, then a decision is reached. So we have this long theorem with a long precondition for liveness, for reaching a decision. And this precondition is exactly what round synchronization is. So if we meet this precondition, we can ensure that at least hot stuff will guarantee progress. So we know that hot stuff makes decisions with a linear message complexity per decision. You also know it needs round synchronization to get this result and work. So if we had a round synchronization module to hot stuff, we get a complete SMR, Byzantine SMR solution. Like I said, hot stuff solves, makes decision with linear message complexity. Round synchronization is actually the bottleneck. And we give an algorithm that solves round synchronization with linear message complexity or expected linear message complexity since we use randomization. And again, we use randomization to circumvent the non-deterministic lower bound, which is quadratic. But it's still important to note the SMR guarantees are still deterministic. So the solution is still deterministic. It's not probabilistic. We only use randomization to improve the performance of it. Okay, so like I said, in the paper, you can find a formal definition of what round synchronization is as a separate problem. We also give an algorithm that solves this round synchronization with a relay-based system. Basically, instead of all-to-all communication, you get a relay-based all-to-a-relay and relay-to-all messages. This is the first SMR algorithm with expected linear message complexity and also expected constant latency, even facing with Byzantine failures. And this is exactly the missing ingredient we need to allow protocols like hot stuff to solve SMR with this expected linear message complexity. So thank you very much, and I'll be happy to take questions.
Thank you, Odette. So maybe let me ask a question. So you claim only static security because the schedule is public, basically?
The what is public, sorry?
The randomness schedule, basically the randomized schedule is known in advance, right?
Yes, but actually we will have a journal version which will also be able to solve it under semi-adaptive adversary. But yeah, for this version, it's against a static strong adversary, yes.
Yeah, so you answered my question without me having to ask it, so that's nice.
So because it's SMR, it's easier because if you take an average on all the cases, you have an infinite number of cases. It's SMR, not a single shot. Therefore, you can also have nicer results.
Do you have to strengthen your assumptions for that, or is it under the same assumptions?
No, we actually don't have to strengthen the assumptions.
Okay.
We have to, it depends on the definition of the performance. So you can define a message complexity based on the worst case, based on the average case. Again, it's a bit, I don't have much time to explain, but it depends on the definition.
Mm-hmm. So Andre asks, do I understand correctly that your protocol will eventually elect the correct leader? That is not just with probability 1.
Yes, the protocol is deterministic. In the worst case, it will have worse than linear message complexity, but the guarantees are still deterministic. We always make decisions.
Okay, thanks, Odette. Let's transition to the next talk, which is about the paper Asynchronous Reconfiguration with Byzantine Failures. This work is by Petr Kuznetsov and Andrei Tonkic, and Andrei will be giving the talk.
Yeah, thank you for the introduction. In this presentation, I will give you a brief introduction to the problem of asynchronous reconfiguration in the presence of Byzantine failures. This is joint work with Petr Kuznetsov. Consider a set of replicas that, consider a set of clients that communicate with a collection of servers, which we also call replicas. The servers implement a distributed object and the clients operate on that object. Such protocols are typically based on the assumption that a certain fraction of replicas do not fail and follow the prescribed protocol. However, in a long-running system, to maintain this assumption, the set of replicas must be adjusted. Replicas that are suspected to have failed should be removed from the system, and new fresh replicas should be introduced. This process is called reconfiguration. Early implementations of reconfigurable storage systems relied on consensus, but later it was discovered that replicated services that otherwise don't require consensus can be reconfigured in a purely asynchronous way. More recently, a lot of progress was made in defining abstract asynchronous reconfiguration in a simple and efficient way, but all these solutions assume benign crash failures. The only comparable solution tolerating Byzantine failures assumes a trusted administrator. But is it possible to implement asynchronous Byzantine fault-tolerant reconfiguration without a trusted administrator? Let us see why this is not trivial. So one of the problems that we need to address is called the I still work here attack. Let us see how this attack works. One of the main reasons for adding new replicas to the system is to increase fault tolerance. However, this may lead to the situation when too many replicas in some old configuration become Byzantine. If some client will try to reach out to such configuration, there will be no way to stop the Byzantine replicas from deceiving the client about the state of the system. So to render compromised replicas in old configurations harmless, we use a cryptographic primitive called forward secure digital signatures. It allows us to create an infinite sequence of private keys with only one public key, which can be used to verify signatures made by any of the private keys. Each replica then associates a single private key with each configuration. Before moving to a new configuration, the replica destroys the private keys associated with previous configurations. Thus, even if all replicas in some old configuration are compromised, they won't be able to process client requests because they will not have the corresponding private keys. Let's now consider some of the challenges posed by the presence of Byzantine clients. An obvious attack for a Byzantine client is to issue a reconfiguration request to a completely compromised configuration. To prevent this, we introduce an access control mechanism. Each request must be validated by a quorum of replicas from an active configuration. Additionally, we need to design the reconfiguration protocol carefully so that Byzantine clients cannot interfere with it. For example, they cannot create a fork in the history of configurations. Finally, we need to deal with concurrent reconfiguration requests. For this, we use a weak alternative to consensus called lattice agreement, which can be implemented in a purely asynchronous way. Even though the processes may not agree on the exact sequence of configuration changes, lattice agreement guarantees that all configurations that are used to serve client requests are totally ordered. As a result, the replicated object appears correct to the clients despite ongoing reconfigurations. So in the paper, we discuss these and other challenges of asynchronous Byzantine fault-tolerant reconfiguration and present solutions to each of them. Finally, we apply these solutions to implement reconfigurable lattice agreement and storage. For more details, you're invited to watch the full video on YouTube and to read the paper in the proceedings and the extended version published on arXiv. Thank you. I'll be happy to answer any of your questions.
What would be a typical condition under which a replica would be replaced?
So there are many potential applications. One of them is permissionless systems, where you have, for example, proof of work, or perhaps like proof of stake system or whatever, and you add replicas according to these conditions, add and remove replicas. And another approach is for like more managed case. In this case, you may want to replace a replica because it is slow, or you may want to replace all replicas if you, for example, suspect that some of them is faulty, but you don't know which one exactly. You can issue a configuration request that completely changes the set of replicas, for example.
Thanks.
I have a question. So what percentage of faulty processors can you tolerate?
1/3 as optimal for storage. Yeah, in active configurations. In configurations, yeah.
Thank you.
So can I ask a question?
Yes, please.
Yeah. So what other applications do you think of implementing with lattice agreement except for the register or storage?
So we primarily implemented lattice agreement because we use it in the reconfiguration protocol itself. But there's a paper by Petr Kuznetsov and others about applications of generalized lattice agreement. In this paper, we only implement not generalized, but usual lattice agreement, but it can be made generalized with some simple modifications.
What's the difference between generalized and not generalized lattice agreement?
In generalized lattice agreement, every proposed value is guaranteed to eventually be part of the decision. In just lattice agreement, not generalized, it is guaranteed only if the number of proposals is finite. Yeah, in any infinite execution.
It's the difference
so
between
it's a liveness. It's
Yeah.
a liveness property. Okay, thank you.
More or less the difference between one shot and long lived.
Yeah, exactly.
So the next talk is about, it's a brief announcement, Byzantine agreement, broadcast and state machine replication with optimal good case latency. This is work by Itai Abraham, Kartik Nayak, Ling Ren, and Jolun Xiong. And Jolun is giving the presentation.
Yeah, thanks for the introduction. Can everyone hear me? Yeah, so I'll talk about good case latency for the next several minutes. So our work is motivated by permission blockchain systems where state machine replication protocols are essential building blocks. So previous speakers already did a great job in introducing SMR. So here I just want to mention that most of the SMR solutions are leader-based. So they can drive consensus decisions very fast under a good leader. But when the leader is malicious and not following the protocol, a view change will be triggered to replace the leader. And the view change is usually costly and slow. So in practice, the overall performance of SMR largely depends on the performance under a good leader. So this motivates our work to further investigate the performance of BFT protocols such as latency under the good case. So we believe the good case latency is an important metric to study for BFT protocols such as SMR. The traditional literature mostly focuses on the worst case latency of BFT protocols, so which is lower bounded by F+1 rounds for Byzantine broadcast and agreement. But the worst case scenarios do not capture the common good case, where the protocols may finish much faster on the good leader like in SMR. So we define and study the notion of good case latency, where the network and local computations are fast, and the leader is honest. So in this paper, we can see the synchronous settings, and we adopt a more refined latency characterization from the literature. we assume the actual message delay is upper bounded by small delta, which is unknown. But there is a pessimistic upper bound big delta, which is known to the protocol designer. And usually this big delta is much larger than the small delta to ensure the safety of the protocol. And we will characterize good case latency in terms of both small delta and big delta. So this table summarizes previous results and our contributions. The good case latency is previously studied in Synchronization, where they propose an SMR protocol with good case latency 2 big delta plus 1 small delta. They also have a lower bound of 1 big delta for BB and BA. So our paper further reduces the good case latency to 1 big delta plus 2 small delta for BB, BA, and the SMR. So our protocol are near optimal if the small delta is equal to 0, which means the network is fast in the good, under the good case. So thanks for your attention, and I'm happy to take questions.
Thank you, Jolon.
Can I ask a question?
Yes, please.
Yeah, so hot stuff already increased the good case latency compared to like traditional Paxos-like protocols in order to avoid the complicated reconfiguration. So are you basically going back a step, or because hot stuff added another round in order to unify the recovery and the normal mode, and
yeah,
for the normal mode we had better performance before that. So. Yeah,
first, hot stuff works under partial synchrony. So in that case, if tolerance is 1/3, here we are talking about synchronous, it's tolerance half. And for any partial synchronous protocols, it's responsive. So it advances with network speed. So which means its good case latency will only have small delta. It may be 3 small delta or 4 small delta, something like that. But under synchrony, there will be a 1 big delta lower bound.
I see. Okay, so the comparison to hot stuff is wrong because hot stuff is asynchronous, is partially synchronous. Okay. Thank you.
We still have time for another question. If not, we move to the last talk of this session. A brief announcement, and the title of the paper is Game Theoretical Framework for Analyzing Blockchain Robustness. And this is work by Paolo Zappala, Marianna Bellotti, Maria Potto-Putucaro, and Stefano Secci. The talk will be given by Paolo.
Thank you. I'm sharing my screen.
Yes.
Okay. So thank you very much. I'm Paolo Zappala, and I'll present this joint work with Marianna Bellotti, Maria Potto-Putucaro, and Stefano Secci. We'll talk about game theoretical frameworks to the analysis of the robustness of blockchains. So specifically, we introduce a new model to understand which are the limits and the boundaries of the number of deviating agents allowed in a protocol. And we provide the tools and a method to analyze specifically the protocols which are made out of independent modules. And eventually we show some of these applications. So first of all, in literature, the concept most used to analyze of attacks is the one of equilibrium. In this case, we show Nash equilibria. So I'll take the example. In this case, we have 3 deviating agents, Byzantine agents. So we choose different strategies with respect to the one recommended by the protocol. And this is a Nash equilibrium because if any of these wants to deviate, our utility is lowered. So this is a stable solution. And in this case, we consider this an attack. So we want to switch from the idea of moving from 1 deviating agent to any possible number of deviating agents and distinguish specifically those agents who behave in a rational or in a Byzantine way. Rational agents are those who want to increase their utility by changing the strategy, while Byzantine agents just they're just performing a malicious strategy. So in the third, there are some concepts which we take, for instance, the one of mechanism, which is a pair of a game and a joint strategy, which is the strategy recommended by the protocol. And we set at K and T, two indices, the maximum number of rational and Byzantine agents. So K resilient is a concept known in literature, while T immunity we introduced there is already the concept of T immunity, but we introduced a new definition which we find is more suited for this analysis. So the method is to divide all independent components, analyze them separately, and then use an operator composition of games, which we have introduced, which consists basically in playing more games at the same time. And we prove that the properties are preserved with this operator. So with this method, we analyze different protocols shown in picture. I provide just an example to show how it works. So, for instance, we have the cross-chain swap, which allows to exchange two assets belonging to different blockchains. So this is a simplified version of the protocol. We can distinguish the steps that perform in the first blockchain to the one performing the second blockchain. So we can give different colors in this case, and separate the two parts in the steps up on the blockchain which they are applied. Since they're independent, because the two blockchains are independent, we analyze them with two different games. This is the game tree. And we provide the properties, and then thanks to operator, we introduce the composition of game. We prove that the whole protocol is robust enough. So summing up, we introduce a new model, and we provide the tools and the methods in the full paper to analyze them. And we provide some of this application and want to extend, hopefully next works to more general protocols. So thank you very much.
Thanks, Paolo. There is time for a short question. Otherwise, I close the session, and I'd like to thank all speakers again.